So good morning students. Here we start with chapter 7 which is the deadlocks, and this is the coverage for our week 12. We have already studied the concept of deadlocks in the previous chapter, but in this chapter we are going to study details of the deadlock. So what is a deadlock problem, system model, deadlock characterization, methods for handling the deadlocks, deadlock prevention and avoidance. These are the topics that we are going to cover in this chapter. And the objectives of this chapter are: we want to develop a description of deadlocks which prevents the set of the processes which are executing at the same time from completing their tasks, and to present a number of different methods which should be able to prevent or avoid the deadlocks in a computer system. In the last class we have discussed what is the deadlock. Deadlock is a problem of permanently blocking of a set of processes that compete for the system resources or communicate with each other. The problem of the deadlock arises because of the careless use of wait and signal operations while using the semaphores for the inter-process communication. There is no efficient solution. Deadlock may be involved in some way. It involves conflicting needs for the resources by two or more processes, because processes wants the same resources simultaneously. So here is a problem of the deadlock. Suppose we have two processes, process P1 and process P2, and the system has two tape drives, tape drive 1 and tape drive 2. And we assume that process 1 holds the tape drive or tape drive 1, and it wants tape drive 2 for completing its work. Similarly, process 2 holds tape drive 2 and wants tape drive 1. So none of the processes will be able to complete its work because the resource what they need is being held by the other process. This is a situation of the deadlock. So you can see from here the scenario, the real life scenario of a deadlock. Just like we have the traffic jams, the shared area, which is the crossing area, when many cars try to use that shared crossing area, at the same time they ram into each other, which leads to the long traffic. So this is a deadlock in a real life scenario. Again, we can have another example of a real life scenario, the bridge crossing example. Suppose we have a narrow bridge from which only one car only one car can cross. So suppose if a car is coming from the side, and at the same time another car comes from the opposite side. So what will happen to them? They are deadlocked, because from this bridge only one car can pass. So the subsequent cars which are coming from behind of this car or from this car, they will be lined up. So this is a example of the deadlock situation. So this problem can only be solved if one car backs up. It preempts the lane so that it can be used by only one car at a particular time. So starvation is possible. Starvation means the processes, they are deprived of the resources. So the formal definition of a deadlock is: a set of processes is deadlocked if each process in the set is waiting for the event that only other process in the set can cause. This is the formal definition. So each process, so the process is waiting for an event that only other process in the same set can cause. That means a process is, for example, holding a resource. So the process is waiting for another resource which is being held by the another process, and another process has to release that resource. So that event has to be caused by the another process. Another example with deadlock with the memory is: suppose we have total memory space available with us 200 kilobytes, and the following sequence of events occurs. Process P1 requests 80 bytes. So 200 minus 80 is 120 space is still left. At the same time, process P2 requests for 70 bytes. So 120 minus 70 is 50. So 50 bytes space is still left, right? So okay. Now after requesting for 80 bytes and 70 bytes giving to the process P2, Process P1 requests for another 60 bytes and process P2 requests for another 80 bytes. So both the processes, a deadlock will occur if both the processes will progress to their second request, because not enough amount of memory space is available for either of the process. So we are going to talk about now some formal definitions and some keywords related to the deadlock. Resources, anything can be a resource that a process needs for its execution. A file can be a resource, a printer can be a resource, memory can be a resource, anything any hardware or a software present within the computer system can be termed as a resource. So a process must request a resource before using it and must release the resource after using it. So the two main functions caused by the process are request and release. Requesting a resource before a process wants to use it, and then after using the resource it must release the resource. Process may request as many resources as it requires to carry out its designated task. So there is no limitation to the number of resources a process can use. The number of resources requested may not exceed the total number of resources available in the system. So for example, if the total number of printers available with the system are 2, a process cannot request for 3 printers. This is what we mean. So if a process cannot request for 3 printers if the system has only 2. Alright, now going to the system model, we will talk about a few definitions and again few terms. Resource. Resource is designated while we are making a resource allocation graph. In this chapter we will be making resource allocation graph. While we are making a resource allocation graph, the symbols R1, R2, R3, they stands for the resources. Resources can be anything. It can be CPU cycle, it can be memory space, it can be input output device, anything. Each resource type, Ri, resource type is denoted by Ri or Rj, has Wi instances. That means, for example, we have a resource called printer. A resource called printer with the system. So if there are 2 printers available with the system, we call that the resource printer has 2 instances. For example, if system has 3 hard disk drives, so the resource type is hard disk drives and the number of instances are 3. Now each process utilizes a resource as follows. First of all, it requests, then it uses, and after using it releases. The last step is done so that the resource is made available to the other processes. Now what are the conditions for the deadlock? What are the conditions required for a deadlock to happen? There are 4 conditions, and these conditions, all these 4 conditions must be true at the same time for a deadlock to occur. If any one of this condition is false, deadlock will not occur. So all these 4 conditions have to be true at the same time. When all these conditions hold true at the same time, deadlock will occur. Now what are the conditions? First one is mutual exclusion, second is hold and wait, third is no preemption, and fourth one is circular condition. All these 4 conditions must be true at the same time for a deadlock to occur. So let's go ahead and just check what are these conditions. Mutual exclusion we have already discussed in the previous chapter. Only one process can have exclusive control of a shared resource. So that means no 2 processes can hold a shared resource at the same time. And if any other process requests the particular resource, then it has to wait unless and until the process releases that resource. So for example, if P1 and P2 both need the printer and there is only one printer available with the system, so let's assume the printer is given to, first of all, process P1. Process P1 and P2 cannot hold the printer at the same time. It must be given to the only one process. So let's assume printer is given to process P1. After finishing the task, process P1 will release the printer and then it will be allocated to P2. This is called as mutual exclusion. Hold and wait. Hold and wait means a process is holding a resource and waiting to acquire another resource that is currently held by a process. Suppose process P1 is holding the resource printer and it is waiting to acquire tape drive which is currently being used by process 2. This is called as hold and wait condition. Process is holding a resource and waiting for the another resource that is used by another process. No preemption. So preemption is not allowed. That means resources cannot be preempted. It cannot be taken back from a process forcefully. A process will release the resource voluntarily after the work has been done. So a resource can be released only voluntarily by the process holding it after the process has completed its task. So preemption is not allowed. Last one is circular wait condition. Circular wait condition makes a chain of the processes. Process 1 holding a resource 1 and requesting for resource 2. Process 2 holding a resource 2 and requesting resource 3, like here. Process P3 holding resource 3 and requesting resource 4. Process P4 holding resource 4 and requesting for resource 1. So if you see, there exists a chain of the processes, a circular chain of the processes in which each process is holding a resource and it is requesting a resource which is being used by the next process in chain. This is called as circular wait condition. So all these 4 conditions must be true at a particular time for a deadlock to happen. So this is the same duplicate slide. Alright. So resource allocation graph, how we construct a resource allocation graph. The graph consists of vertices and the edges. So same way, resource allocation graph consists of vertices and the edges. Now vertices are partitioned into 2 types. Vertices can be processes, all the processes and all the resources. So the 2 type of vertices that will exist in the resource allocation graph, they are the processes and the resources. So P stands for all the processes in the system and R stands for all the resources in the system. Now there are 2 types of edges. We are going to consider it as a directed graph, not an undirected graph. So request edge, when a process is requesting for a resource, that is a request edge. When a resource is allocated to a process, that is called as the assignment edge. So in the assignment edge, the edge goes from resource to the process. In the request edge, the edge goes from the process to the resource. So if I go back to the circular chain where I showed you this one. So if you see over here, the resource RA, because the arrow goes from resource to the process. So that means this is a assignment edge. RA is assigned to process P1. Now this edge goes from process to the resource. So that means process is requesting for resource RB. Now coming to resource RB, now edge goes from resource to the process 2. So this is a assignment edge. Now here this edge goes from process 2 to resource RC. So this is a requesting edge. The requesting edge always goes from process to the resource. Assignment edge always goes from the resource to the assignment. So these are the 2 types of the edges. Now 4 conditions, these are modeled by using the shapes. What are the shapes that we are going to use? Process will be depicted by a circle. Resource will be depicted by a square, and this dot symbol indicates the number of instances of a resource. Suppose I say that there are 3 printers available with the system. So when I draw a resource, I will draw the resource printer as like this. So let me name it as resource printer. And when I say there are 2 instances of the resource printer, I will just draw 2 dots. So these 2 dots means that there are 2 printers available with the system. 3 dots here means that there are 3 instances of particular resource available with the system. So number of dots indicates number of instances of a resource. Requesting a resource, so the edge goes from process to the resource. and assignment edge goes from the resource to the process. So when the edge goes from resource to the process, it's an assignment edge. Okay, going further. So example of a resource allocation graph over here. Now first of all, let's analyze the graph over here. Let's first of all analyze the Alright, so first of all let's understand this graph. Now this is a graph consisting of process, resource and edges. Now what are the process? There are three processes: process P1, process P2 and process P3. And there are four resources: resource R1, resource R2, resource R3 and resource R4. Resource R1 has only one instance, resource R2 has two instances, resource R3 has one instance, resource R4 has three instances. Now let's talk about the edges. P1 to R1, that means process P1 is requesting for a resource R1 and instance of a resource R2 is given to process P1. Then coming over here, resource R1 is given to process P2 and resource R2 is also given to process P2. Process P2 is requesting for an instance of a resource R3. Resource R3 is given to process P3. Resource R4 is not at all used. So this is how we can understand the graph. Now let's understand over here whether there is a cycle or not, or whether there is a deadlock or not. Given the definition of a resource allocation graph, it can be shown that if the graph contains no cycle, then no process in the system is deadlocked. If the graph contains a cycle, then a deadlock may exist. So for example, over here, there is no cycle. A cycle means a complete circle of the arrows if it exists. So there is no cycle in the graph over here, so there is no deadlock. So if the graph contains no cycle, then no process is deadlocked. So going ahead over here, going to this slide. Now what the graph is the same, just what is the change that have been done over here. In the previous graph, resource 3 was just process 3 was just having the resource 3, holding the resource 3, but it was not requesting for any resource. Now in this case, process P3 is requesting for a resource of instance of a resource R2. Now let's check over here whether we have a cycle or not. We have two cycles in this graph. So from P1, R1, P2, P2, R3, P3 and R2. This is the first cycle, and then we have the second cycle, P2, P2, R3, P3 and R2 and then P2. So these are the two cycles that exist over here. Now whether this is a deadlocked or not, this is a deadlock, because if you see over here, process P1, P2 and P3 are deadlocked. So how they are deadlocked? Process P1 is holding a resource R2. It requests for resource R1. Now this resource R1 is being used by process P2. R2 is also given to process P2. But process P2 is requesting for a resource R3. But R3 is being used by process P3 and P3 is requesting for a resource R2 and none of the instance is free. So in this case, process P1, P2 and P3, all the three processes are deadlocked because P1 is waiting for the resource R1, which is held by the process which is held by the process P2. Then P2 is waiting for the resource R3, which is held by the process P3, and P3 is waiting for the resource R2, which is held by the process P2. Hence, this is a deadlock condition. So there is a cycle in the graph and hence there is a deadlock. So the first condition that you can know whether there is a deadlock or not, If there is no cycle in the graph, no deadlock. If there is a deadlock, if there is a cycle in the graph, then deadlock may exist. I'm not saying over here that there is a deadlock. So then the deadlock may exist. In that case, you have to find out that whether there is a deadlock or not. In the next slide, I will give you an example where there is a cycle but still there is no deadlock. Alright, so let's see over here. We have two resources, R1 and R2. R1 has two instances, R2 has two instances. We have four processes, process P1, process P2, process P3 and process P4. Now if you see over here, process P1 is holding resource R1 and it is requesting for a resource it is holding resource R2 and it is requesting for a resource R1. Same way process P2 is holding resource R1 but it is not requesting for anything. Process P3 is also holding resource P3 but it is requesting for a resource R2. Instance of resource R2 is given to process P4. Now if you see, there is a cycle from P1 to R1, then P3, then R2, then P1. There is a cycle. This cycle exists over here. But there is a no deadlock, because if you see, process P1 is requesting for a resource R1. Process P2 is holding resource R1 but it is not requesting for anything. So what will happen? Process P2 will finish its work. As soon as process P2 has finished its work, resource R1 can be allocated to process P1. Then process P1 can do its task and release the resource 2. Similarly, when resource 2 is released, it can be given to the process 3 and process 3 can do its task. Or alternatively, process P4 is not requesting for anything. So when process P4 is done, resource R2 can be given to the process 3. So there is no deadlock, because if you observe, P4 may release its instance of resource type R2, then this resource can be allocated to process 3, breaking the cycle. So in summary, if a resource allocation graph have a cycle, does not have a cycle, then the system is not deadlocked. But if there is a cycle, the system may or may not be in a deadlock state. This observation is very important when we deal with the deadlock problem. So when there is no cycle in the graph, no deadlock. But when there is a cycle, there may be a deadlock. So when is the deadlock condition? If there is a cycle, what is the condition there will be a deadlock? If a resource has only one instance type, then it may lead to a deadlock. If there are several instances of a resource, then possibility of a deadlock. If I go to the previous example, here only we have two resources, but both the resources have two instances. If the resources have multiple instances available, then there is possibility of a deadlock. If I go over here, all the resources, resource R1, resource R3, they have only one instance. Only resource 2 has two instances. So if a resource has one instance and there is a cycle in the graph, there will be a deadlock. But if there is a cycle but there are resources with multiple instances, there may be a possibility of a deadlock. So these are the conditions which have to be taken care of while we are analyzing or drawing a resource allocation graph, and all these points have to be mentioned in the answer when you are writing an answer to explain whether there is a deadlock or not. So first thing you need to explain is a cycle, and second thing you need to explain is number of instances of So based on these two conditions, you can check, you can analyze the graph and write your answers. Alright, now moving ahead. Now how to deal with these deadlocks? We can deal with the deadlock problem in one of the three ways. So we have three ways for handling the deadlock. We can use a protocol to prevent or avoid deadlocks, ensuring that the system will never enter into a deadlock state. We can allow the system to enter into a deadlock state. We detect the deadlock and then we have some recovery techniques. Third thing is we can ignore the problem altogether and we pretend that deadlocks never occur in the system. This third solution is the one which is used by most operating systems, that they ignore the problem altogether of the deadlocks. They pretend that deadlocks never occur in the system. This is used by Linux and Windows, and then it is up to the application developer to write a program that handle the deadlock. So application developers, they are incorporating or embedding in their applications the methods of handling the deadlocks. So to ensure that deadlocks never occur, systems can use either a deadlock prevention or deadlock avoidance. So there are two techniques: deadlock prevention or deadlock avoidance. Deadlock prevention means provide a set of methods to ensure that at least one of the four necessary condition is false at a time. So one of the four necessary condition cannot hold. So if any one of the four necessary conditions, the four necessary conditions are a mutual exclusion, hold and wait, no preemption, and circular wait. If any one of these conditions is made false, deadlock will never happen. So deadlock prevention means we have certain techniques, certain methods, and we ensure that one of these technique or the condition cannot hold. So these methods prevent the deadlock by constraining how requests of the resources are made. Deadlock avoidance. Deadlock avoidance requires that operating system should be given additional information in advance concerning the resources a process will request. So avoidance requires certain techniques which the process, so when a process wants to execute, before executing it must give the information to the operating system regarding its resources. What are the type of resources a process needs, how many resources a process needs. So these are certain things a process should tell the operating system before it starts its execution. With this additional knowledge, operating system can decide for each request whether or not the process should wait or not. To decide whether the current request can be satisfied or delayed, the system must consider the resources available at a particular time and the resources currently allocated to each process and the future request. So by knowing the resource requirement of each process in advance, operating system can carefully allocate the resources to the processes and hence deadlock can be avoided. If a system does not employ either a deadlock prevention or a deadlock avoidance algorithm, suppose none of algorithm is employed in a system, then how to handle a deadlock situation? So then a deadlock situation may arise. In this environment, system can provide an algorithm that examines the state of the system to determine whether the deadlock has occurred, and then it will have an algorithm to recover from that deadlock. So if neither of the techniques is available, then if the system goes into the deadlock, then the operating system will have an algorithm to recover from the deadlock. So deadlock prevention. Deadlock prevention means one of the four conditions should be made false. So how to make the four conditions false? How to make that mutual exclusion should not hold, or second condition which is hold and wait should be made false, or third condition which is no preemption should be made false, or the fourth condition which is circular wait should be made false. So we know that so by ensuring that at least one of these conditions cannot hold, we can prevent occurrence of a deadlock. Mutual exclusion. Mutual exclusion condition must hold. The mutual exclusion condition should be there, that is at least one resource must be non-shareable. That means there should be at least one resource in the system which is not shareable, non-shareable. Shareable resources do not require mutually exclusive access, and thus cannot be involved in a deadlock. So if our resources are shared, for example, there are two instances of the printer which can be shared, they do not require mutually exclusive. For non-shareable resources require the mutual exclusion. Read-only files, they are the good example of the shareable resource. If several processes are trying to open a read-only file at the same time, they can be given a simultaneous access. So a process will never need to wait for a shareable resource. So this is how mutual exclusion condition must hold. Hold and wait, to ensure that hold and wait condition never occurs, we can make this condition as false. We must guarantee that whenever a process is requesting for a resource, it is not holding a resource. So for example, if a process P1 has requested a printer, the operating system must make sure that it is not holding any resource. So what is the protocol? The protocol used is requires each process to request and be allocated all of its resources before its execution begins. So what is the policy that can be followed by the operating system? That before the execution begins, a process requests and gets all the resources allocated to it before it starts with the execution. This can be done by using the system calls, requesting a resource for the process and giving it. Another alternative protocol or the system is which allows a process to request a resource only when it has none. So this is another protocol. So a process can request for a resource when it has no resource under it. So for example, a process P2 is executing. Process P2 is requesting for a tape drive. Tape drive can be given to process P2 if it is not holding any resource. In that condition, when it has none, it is having none of the resource. A process may request some resources, use them, but before it can request any additional resources, it must release all the resources which are currently allocated. So for example, if a process P2 is using a tape drive now, then it wants to make request for a printer. Now when the process P2 requests for a printer, it must make sure that it has used the tape drive and it has released it, then only the printer will be allocated to the process P2. So this is how hold and wait condition can be prevented. That means if a process is holding a resource, it will not be allocated any other resource. This is the bottom line. No preemption. No preemption means preemption not allowed. So the third necessary condition for deadlock is that there should be no preemption or the release of resources that have already been allocated. So how to ensure this? To ensure this condition does not hold, we can have the following protocol. If the process is holding a resource and requests another resource, it cannot be immediately allocated to it. So all the resources the process is currently holding are preempted. So for example, if a process P1 is requesting for a printer but it is holding tape drive and hard disk at the same time, because it has requested for a printer, it will not be given to the process P1 unless and until all the resources that it is requiring, it releases all the resources. That means the preemption is allowed now. In other words, these resources are implicitly released. So the preempted resources are then added to the list of the available resources which can be given to the processes which are waiting for these resources, and the process will be restarted only when it has regained all its old resources. So alternatively, no preemption. If a process requests for some resources, we first check whether they are available. If the resources are available, we allocate it to the process. But if they are not available, we check whether they are allocated to some other process that is waiting for the additional resource. If they are available with some other process, we preempt the desired resource from the waiting process and allocate it to the requesting process. So if resource is not available and it is not used by some waiting process, the requesting process must wait. That means the resource is either not available or it has been used by some it is being used with some other process. So while a process is waiting, some of its resources may be preempted, but only if another process has requested it. Now, when a process can be restarted only when it is allocated the new resources it is requesting and recovers any resources that were preempted. So for example, I take an example. Process P1. Process P1 is holding a tape drive. Let's assume that, let's talk about no preemption. So let's assume that it is holding a tape drive, it is holding a fax. I'm going to talk about two conditions, what the conditions that are explained over here. So process P1 is holding these two. Now it is requesting for a printer. Requesting for a printer. Now what operating system will do? It will check whether the printer is being used by some process or not. If the printer is used by, for example, process P2 is holding a printer, but it is also waiting for some other resource. Let's assume that process P2 is waiting for some maybe tape drive. Alright, so in this case what will happen? This printer will be preempted from process P2 and it will be given to process P1, which is explained in the first paragraph. So this is the first condition what will happen. So if a resource is used by some waiting process, then the resource will be preempted and it will be given to the requesting process. So this is what line. We check whether it is allocated to some process that is waiting for additional resources. If so, we preempt the desired resource and allocate to the requesting process. Now if the process is neither available, now let's assume that it is not available and it is not held by some waiting process. That means we have some other process P3 which is using the printer. Now which is using the printer. So while this process P1 is waiting, some of the resources may be preempted, maybe because process P2 is waiting for the tape drive. Now process P1 is waiting for the printer. So what may happen? This tape drive can be preempted from the process P1 and it can be given to the process P2. So process P2 can finish. Now this process P1 is in a waiting state or it is held. Now this process P1 will restart again only when it gets its tape drive back and printer back. So this is how what is explained. This is what it is explained in the last line. A process can be restarted only when it is allocated the new resources, which is the printer it is requesting, and recovers any resources that were preempted while it was waiting. So the resource that was preempted from the process P1 was tape drive. It was given to the process P2. So the process P1 will start only when it gets its tape drive back, also when it gets the printer resource that it has already requesting. This is called as no preemption. That means preemption is allowed now. Circular wait. So the fourth and final condition of the deadlock is the circular wait condition. One way to ensure that this condition never holds is to impose a total ordering of the resource type. That means the resources that are available with the operating system, we make an ordered list of the resources and we require that each process requests resources in an increasing order of enumeration. Now what happens over here is resources are given some number, given some priority number or given some number. And now it is required that when a process is requesting for a resource, it requests in the increasing order of enumeration. So what is increasing order of enumeration? I am going to explain it. Suppose to illustrate this, we have resources R1, R2, Rn be the set of the resources. So here in the example, we have three set of resources: tape drive, disk drive and printer. We assign each resource type a unique integer which allow us to compare the value of the resources and to determine one precedes another in our ordering. So here we have given some value to the resources. So for example, integer number, tape drive has a value 1. Higher the integer value, higher is the ordering. Disk drive has number 5, printer has number 12. Then we define one-to-one function, resource to a number. So this is a one-to-one function. No two resources can have the same number or the same ordering, where n is a set of natural numbers. For example, if the set of resource type R includes a disk drive and printers, then the function f might be defined as follows. So function is tape drive is given number 1, disk drive is given number 5, and printer is given number 12. Now, circular wait, we can now consider the following protocol to prevent the deadlock. What is the protocol, or what is the bottom line here? Each process requests for the resources only in an increasing order of enumeration. That means if a process has initially requested for a resource, say Ri, then the process can request for an instance of a resource Rj if the value of Rj is greater than Ri. That means the number in Rj should be greater than Ri. Ri is the resource previously used and Rj is the resource requesting after Ri. So for example, using the function defined in the previous, a process that wants to use a tape drive and a printer at the same time must request the tape drive and then request a printer. So for example, if I go back, if a process wants to use tape drive and a printer, it cannot just ask for a printer first and then go to the tape drive. First of all, a process must request for a tape drive, then only it can request for a printer. So a process always requests for the resources in the increasing order of the enumeration. So alternatively, we can require that a process requesting an instance must have released the resource Ri, which has a lower enumeration value as compared to the Rj, and if these two protocols are used, then circular wait condition cannot hold. So this is the way how we can deny the circular wait condition. Deadlock. Now we come to the deadlock avoidance. Deadlock prevention algorithms prevent deadlocks by limiting how requests can be made. So this ensures that at least one of the necessary conditions cannot occur. There can be possible side effects which can be low device utilization and throughput of the system can be reduced. These are some of the disadvantages of the deadlock prevention. But we have an alternative method for avoiding the deadlocks is to require the additional information about how resources are to be requested. For example, if in a system we have one tape drive and one printer, system might need to know that a process will request first tape drive and then printer before releasing both the resources, whereas process Q will request first printer and then the tape drive. So deadlock avoidance means operating system needs to know in advance the requirements of the resources of a process. So here in the example, it is assumed that there is only one tape drive and one printer, and we have two processes P and Q, and both of them want these two resources. So in that case, process P should use first tape drive. Process P should use tape drive first, and process Q should use printer first. After Q has used printer first, printer will be allocated to the process P, and after P has used the tape drive, it can be allocated to the process Q. This is how deadlock can be avoided. So but for this, operating system needs to know in advance the requirements of the resources of a process. So with this knowledge of the complete sequence of requests and releases for each process, the system can decide for each request whether or not a process should wait to avoid a future deadlock, and each request requires that making this decision in the system consider the resources carefully. So the resources which are currently allocated to a process, and it can also consider the future request and releases of a process. So this requires a prior knowledge of the resources which will be needed by the process, and hence deadlock can be avoided. Now, if a system does not employ either a deadlock prevention or a deadlock avoidance, then deadlock may occur. So in this environment, if a deadlock occurs, what the system will do? In that case, system will provide some algorithm or a procedure which will examine the state of the system, and it will check whether deadlock has occurred. And if a deadlock has occurred, this algorithm will help the system to recover from a deadlock. So this is a situation, let the deadlock occur, we have an algorithm, we have a procedure, we will make the system recover from a deadlock. So this is the third option if we don't have any deadlock prevention or any deadlock avoidance algorithm. This is called as deadlock recovery. So let the deadlock happen, we have the algorithm for deadlock recovery. So when a detection algorithm determines that a deadlock exists, several alternatives are available. One possibility is we inform the operator deadlock has occurred and let the operator deal with deadlock manually, just like we sometimes do. You might have experienced sometimes when you open many applications or many tabs of the browser window, at a particular time your system becomes irresponsive or something like that. So in that case you restart your system, that is, operator is dealing with the deadlock manually. Another possibility is to let the system recover from the deadlock automatically, and there are two options for breaking a deadlock. One is simply to abort one or more processes to break the circular wait, and the other one is to preempt the resources from one or more deadlock processes. So this is automatically. What are the two options taken by the system to recover from a deadlock automatically? First one is simply abort the system, shut off the system and break the circular wait, and another one is release some resources or take back some resources from one or more deadlocked processes. So this was all about the deadlock recovery. So these are the two simple protocols or the algorithms which are followed in the deadlock recovery. In the class I will discuss some questions or some problems based on the resource allocation graph, and I will be solving those questions with you. So thank you so much. Please listen to this chapter and please come up with your questions in the class on Sunday.